Okay, so we're in the next video now, AP Physics C Prep Day 1, Part 9. This is where we start actually talking about derivatives and a strongly related factor called tangents. Now I'm going to go into a little bit of physics, even though this is supposed to just be the calculus part of calculus preparation for physics. I want to introduce you to something that you run into in physics but you don't run into in math a whole lot, and that is unusual labels on your axes. Usually in physics you're not plotting x against y. You do occasionally, but more often the thing on your horizontal axis is going to be time, usually abbreviated t. Now, x and y are variables that are used for positions, either on two different axes. It doesn't matter which axis you call x. But as I said in a few videos ago, position can change with time. So position is actually a function of time. And since it's a function of time, since it is a dependent variable, a variable which depends on time, it belongs on the vertical axis. And the independent variable, the variable which proceeds along without being affected by the dependent variable, that belongs on the horizontal axis. So this is going to be a little confusing for the first few slides, and I do skip around in my notation on this. Following this video, there'll be a series of videos from Khan Academy, which uses a much more consistent notation, but I want to introduce you to the broader world of independent and dependent variables, rather than just x's, y's, and f of x's. So, anything that's an independent variable can go on your x-axis. Anything that's a dependent variable can go on your y-axis, or better call it your horizontal axis and your vertical axis, including something that we call x, because x is the abbreviation that physicists use for position. Okay, so let's say we have an object, this green ball that just appeared here. And if we're actually watching this ball, we throw it straight up, and anything that goes up must eventually slow down and then eventually start falling. And so if you plot its position as a function of time, you get a graph that looks like this. Okay, so we throw it upwards, and it moves up a bit to this point, and so time progresses a bit, and position increases a bit. Time progresses a bit more, and position increases a bit more. Time progresses more, position increases more, but not as much. You notice that each change in each increment of time gives you a smaller increment of a smaller increase in position. And eventually, we're going to go up and hit some sort of peak of our motion, and then we're going to start moving back downwards. So this is a motion where the object goes up and then it goes back down a little bit. And then the peak of the motion is somewhere here, or somewhere at this position here, and at this time point right about there. Okay, so what is a tangent? Well, a tangent, in order to understand what a tangent is, you have to first understand what a secant is. So a secant, otherwise known as a secant line, or a secant is a line connecting 2 points on a graph. So take one point that we care about. Call it horizontal position t, vertical position x. Take another point that we don't care about. Call it x0, t0, or sorry, actually it would be better described as t0, x0. Okay, draw a line between them. This white line here, that's a secant line. It is a line connecting 2 points on a graph, any 2 points. Now the slope of this secant, on this graph of position versus time, is going to be the average velocity, not the velocity, the average velocity from t0 to t, from this time point to this time point. Within that domain, our average velocity was this, was the slope of that secant. Now, a tangent is a secant with a time span of 0. Okay, so what we can do is we can start bringing the point that we don't care about closer to the point that we do care about. And you notice, as we do that, the slope of this line, this secant line, changes. Now, we currently have a time span that is not 0. So this secant line here is still a secant line. It is not yet a tangent line. So let's get it a little closer. Okay, we still have some non-zero span here. So it's still a secant. Let's get it a little closer. Still have some non-zero span here. And also the slope of this line, the slope of this secant line, is going to be the average velocity. But now it's going to be the average velocity for this time span rather than what we originally had of this whole time span from the origin to t. So it makes sense that the slope is changing because we're changing the time span. All right, eventually when you lay the t naught on top of t and x naught on top of x, basically you continue that trend that you made by making secants with smaller and smaller time spans. Then you get a line like this, and this line is a tangent. It is a line that captures the rate of change right around your point of interest. And the slope of the tangent is velocity at time, velocity at this particular time that we're interested in. And as I told you before, velocity is the derivative. So the reason we're so interested in tangents is because the slope of the tangent and the derivative are exactly the same thing. The slope of the tangent and the derivative are the same thing. And that's because the derivative is the rate of change and the slope of the tangent is the rate of change as well. All right, you might have heard of the terms secant and tangent in geometry. If you remember this stuff, cool. I'll relate the two together on this slide. If not, feel free to ignore this slide. It might not help you, and hopefully it won't confuse you. Okay, when you talked about circles in your geometry class, hopefully they covered that a secant is any line that connects 2 points on a circle. And similarly on a graph, a secant is any line that connects 2 points on a graph. And then as you make the spans of those secants smaller, you eventually you continue that trend until you have no span. Then you end up with a tangent line. Over here, you have a secant with no span. That's a tangent to a circle. Over here, you have a secant with no span. That's a tangent to the graph. Specifically, in this case, the graph of position versus time. Okay. So let's go back to this definition that a tangent is a secant with a time span of 0. And really firmly relate that back to a derivative, and also at the same time come up with an actual equation that defines what a derivative is. This is the most fundamental definition of a derivative. Incidentally, it's also the least useful, but let's not get into that too much. Okay, so we got our secant. We make the time span smaller. And while we still have some non-zero time span, we can say that the slope of this secant is going to be the difference between the two vertical coordinates, in other words, that point minus that point, divided by the difference between the two horizontal coordinates. So the difference between this point here and this point here, otherwise known as your change in vertical coordinate divided by your change in horizontal coordinate, or rise over run. Anybody who's taken an algebra class should know this. Slope is rise over run. But what if your rise is 0 and your run is 0? In other words, what if you've made this span so close that your two vertical coordinates are equal to each other and your two horizontal coordinates are equal to each other? Well, then you have 0 over 0, and you just saw a whole bunch of limit equations that help you deal with the limit as an equation approaches 0 over 0. Now, in this case, we don't have enough information about what exactly x of t is and what exactly x naught of t is in order to actually solve this. But what we can do is we can at least write out the limit. So we can say that the slope of the tangent, which is the same thing as the derivative, because they both capture a very the rate of change. They both capture the rate of change in this little neighborhood around this point. The derivative is the limit as our 2 points come together of our vertical coordinate divided by our horizontal coordinates, or the difference in our vertical coordinate divided by the difference in our horizontal coordinates. Now, since this is infinitely small, we call this dx, not delta x. D is just like delta, and d are pretty much the same thing, except the d is infinitely small. And this would be 0 if it weren't for the fact that the thing on the bottom is also infinitely small. So something infinitely small divided by something infinitely small can still give you a finite number. And in fact, you can see that this has a slope, and if with a little bit of work, we'll calculate that slope later. And so this will give you a finite rather than infinite number for the derivative at this point. Now, let's go back to math textbook land rather than physics textbook land, where everything on the vertical coordinate is f of x and everything in the horizontal coordinate is x. If you look in any calculus textbook, you'll see a definition that looks like this. The derivative of a function with respect to x, which is, or the derivative of the dependent variable with respect to the independent variable, is the limit as, and they introduced this function h. The h is just the span of your secant. So it's the limit as the span of your secant approaches 0, because remember, tangent is a secant line with a time span of 0. It's the limit as the span of your secant approaches 0 of a point that has your independent variable plus the time span plus the span of the secant minus the value of your dependent variable at your point of interest. So a point really close to your point of interest minus a point at your minus your point of interest divided by the span between these two guys. Again, sorry about the change in notation. I'm trying to introduce a broader range of variables and get you used to that so that you don't freak out when we do this in physics. Unfortunately, it can create a little bit of confusion. Like I said, there's some Khan Academy videos coming up, and they use a much more consistent notation. Okay, so once again, hammering home the fact that the slope of the tangent is velocity, and velocity is the derivative of position with respect to time. Previously, we dealt with just one point, but this is a curve. And a curve is made up of an infinite number of points. Remember, points are infinitely small, so in any span, in any domain, in any non-zero domain, you can fit an infinite number of points. Here I've selected 5 points of interest, and you can draw a tangent line at each and every one of these points. So there's a tangent line right there. And as you can see, this is a very steep line. It rises a lot for very little run. So steep line means it's going to have a very high slope. And remember, this is a tangent, so slope of our tangent is the same thing as the derivative, and the derivative of position with respect to time is the same thing as velocity. So at this point, we got a very high velocity. Now, this tangent that goes through point T2 is moderately steep, and that's going to give us a moderate velocity at time point T2. Similarly, at time point T3, we'll have a shallow line. It will still have positive slope, but it will be a very low positive slope, and that's going to give us a very low but still positive velocity at time point 3. Now, time point T4 here is kind of special, because when you draw the tangent line through here, you get a flat line, a perfectly horizontal line. And the slope of a horizontal line is 0. Okay, so we can say that the derivative, or the velocity, at this particular point is 0. At T4 is 0. And then, once you start getting downhill lines, like you do at T5, then that means that your slope is negative, because for a positive run, you have a negative rise. So our velocity is going to be negative at T5. So we can set up this whole inequality. Velocity is highest, or the derivative, or the slope of the tangent is highest at T1. It's still positive, but a little lower at T2, lower still at T3, lower still at T4, it's 0, and at T5, it's something less than 0. Okay, now let's actually start putting some numbers on here. Based on each of these units being square, you can actually calculate the velocity, and so this has a slope of 2.7. In fact, you can see it pretty much intersects that point, and then for 1 unit of running, you end up with 2 and a little more than half of a unit of rising. So that's going to give you a slope of 2.71. Similarly, over here, you get a slope of 0.69, and right here, you get a slope of 0.36. Right here, as we said earlier, you get a slope of 0. This slope ought to be negative, and yeah, the slope is negative 0.35 meters per second. Okay, now remember back to the second video where I said the rate of change in a function is, in and of itself, a function. And I'll show you how that works here. We have this value of velocity at this particular time, which is about half a second. And then we have this other value for velocity that corresponds to this value of time, which is about 2.5 seconds. And similarly, each of these time values produces a unique velocity value. So we can make another plot where we got velocity, in other words, where we take these points and put them on this axis, and then we still keep the same values of time on this axis. So we'll keep our same 5 values of time. Notice that the time spacing here is the time spacing here, is the same thing as the time spacing here. And that's because this axis is time, and this axis is time. See, they got the same label. Okay, so we're keeping our independent variable the same. We're just changing the dependent variable. Okay, and 2.71, that's 1 unit, 2 units, and a little more than half of another unit. Okay, we can go through the same thing with all of these other values, and we get these points. See, this one's below the horizontal axis, and that reflects the fact that we've got a negative sign here, which reflects the fact that we have a downward slope at the tangent to this line. All right, well, we can connect these points and get another function. So this graph here is the graph of velocity versus time, or the graph of the derivative of position with respect to time, or the derivative versus t. Okay, there is one special case, which in physics would be constant velocity. In any other math course, it would be any sort of straight line. If you have an object moving at constant velocity, like if you have a car on a straight road and you hit the cruise control, your speed doesn't change, your direction doesn't change, so your velocity does not change with time. That gives you a graph of position versus time that looks like this. And if you were to select any 2 points, you could calculate, let's call this one of our points and this another one of our points, and I've used the red line to show a secant line from time t equals 0 to t equals 5 seconds. Actually, yeah, 5 seconds. So 5 seconds is right there. Follow it up, you get a little bit more than 8. Okay, slope of the secant, as we said before, is average velocity, not what we would call velocity or instantaneous velocity, but average velocity from time t equals 0 to t equals 5. All right, so to get the slope of this secant, you do the rise, which is close enough to 8 meters that you could call it 8.0, and then the run, which is exactly 5 seconds, and you do the math, break out your calculator, you can get 1.6 meters per second as your average velocity. Now, if you take any point along this line, the tangent to a straight line is exactly the same thing as the line itself. So that means that the slope of the tangent is going to be your velocity, as it always is. But in this case, we're going to end up with the exact same numbers that we had in the average velocity calculation. And so, not surprisingly, we get the same answer. Okay, so this is a special case of constant velocity or any other linear function. And what makes this special is that the derivative is equal to delta x over delta t. Normally, the derivative is delta x over delta t, but the limit of this as this stuff approaches 0, is particularly the delta t part. Okay, we can use this graphical interpretation of the derivative in order to find out something, in order to prove something that's a little circular in logic, but will make sense in just a moment. Okay, so we take a point, t1, on this motion at constant velocity, and it forms this yellow line that lies directly on top of the white line, so it's a little hard to see, but it's the same line. Okay, same line means same slope, 1.6 meters per second. Okay, so if we were to plot velocity versus time, we would take our time of about here, that looks like about 3/4 of a second. 3/4 of a second, 1.6 meters per second. Cool. Okay, take another point, t2. Draw a tangent to that point. Surprise, surprise, it's the same thing, and we get the same value, 1.6 meters per second. Plot that over here, and you get this point. Keep doing that for t3. And then you get this, all of these points are at the same vertical position, and so you can draw a horizontal line. And this should kind of be circular logic. I set up the case, I called this a special case where you have constant velocity, and so it should not be surprising that you get the same value for velocity at all of these different times. That's what it means to be constant. As you change one variable, you do not change another variable. And so, while, like I said, this is kind of circular logic, it does at least prove that this whole derivative and slopes of the tangent thing is internally consistent. When we set up a system where we have constant velocity and then we take the tangents, then we actually do get constant velocity. Okay, and if velocity is constant, then the plot of velocity versus time is a horizontal line where the position of this line, the vertical position of this line, is the same thing as the slope of this line. Okay, now just to make life really confusing for people who are just starting to learn calculus, there's a lot of different notation used in calculus. And unfortunately, the videos skip among various notations, and the books skip among various notations, so there's really no way around learning a variety of different notations. Okay, so there's many ways to write a derivative. If f is a function of x, then the derivative of f is, first of all, just definition-wise, it's the rate of change in f of x with respect to x. It is the slope of the tangent lines on the graph of f of x versus x. And there's a lot of different ways to write this. The derivative, you could call it df dx, as we've been doing. You could move the f outside of the fraction thingy. So you could say d over dx times the function f. You could say f with this little apostrophe. This is very often called f prime. If you wanted to specify that f is a function of x, you could say f prime of x. And then a slightly rarely used notation is this capital D with a subscript x of f. Now, as I said, in physics we're going to be using a lot of different independent variables, a lot of different dependent variables. In math, you can be pretty consistent about your dependent variable being f and your independent variable being x. But let's go back to a more generalized y and x system. Wherever you see an f, you put in a y. That's the interchangeability of dependent variables. Okay, so anything could get this d dx treatment or a d dt treatment. It can be written this way, it can be written this way, it can be written this way. The only notation I'm not going to use is this last notation, and that is because if you go on to college level engineering somewhere around your junior or senior year, maybe your late sophomore year, you will probably take a class in mass transport, and in mass transport this symbol means something completely different from this. Okay, so I'm going to stick to mostly these first four notations, and when I'm actually doing the writing, I'm actually going to just stick to these first two notations. I'm not going to use the prime notation. Insert joke about transformers and prime here. With that joke over, okay, couple reminders. Remember that in physics, another complication we have to deal with is units. Now, an easy way to figure out what the units of a derivative are is just to remember that it's a slope. It happens to be the slope of a tangent, but it's still a slope. And to calculate slope, you do delta y over delta x, and so the units of slope are going to be the units on your y-axis divided by the units on your x-axis, or the units on your vertical axis divided by the units on your horizontal axis, or the units of your dependent variable divided by the units of your independent variable. Okay, one last special case before we wrap up this video. There's a few cases where derivatives do not exist, and this little graph here shows all three of them. First one is what's called a discontinuity, where your graph jumps, where it is no longer continuous. And that would be this point right here. See right here, we got a point there. a point there, and there's nothing connecting them, so it is discontinuous. Now, if we were to draw a tangent to this point, it would look like that. If we were to draw a tangent to this point, it would look like that. And so there is no one single tangent that represents the both sides of this discontinuity. And so the slope, there is no single value for slope of the tangent at this discontinuity. And so you say that the derivative does not exist at this particular point. And in fact, at all discontinuities, the derivative does not exist. Okay, the next thing is a cusp. A cusp is a really fancy name for a corner, something like this little bit here. Okay? See how those two points come, those two curves come together, and they don't smoothly blend from one into the next. They just kind of slam into each other. Okay? Well, if we take the derivative from one side of the cusp, we get, or if we draw a tangent from one side of the cusp, we get this tangent line. If we draw a tangent from this side of the cusp, we get that tangent line. These tangent lines obviously have very different slopes. Since they have different slopes, that means the derivative, you get different answers for the derivatives from if you approach from this direction versus this direction. And therefore, there is no single value for the derivative at this point. And so you say the derivative does not exist at this particular point. Okay, you got vertical tangents. Over here, if you were to draw a tangent to this point right here, you would get a vertical line. Now, the slope of a vertical line is either infinity or negative infinity. In this case, it's actually negative infinity because if you draw tangents here, 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 in other words, as you keep progressing along the horizontal axis and drawing tangents, you get more and more and more and more negative numbers. And so the limit, as you were to approach this case, would be negative infinity rather than positive infinity. Okay, depending on how strict your teacher is going to be, saying that the derivative does not exist may or may not be acceptable for vertical tangents. Some teachers will require you to say that the derivative is positive infinity or negative infinity, or there are some cases where it does not exist. To distinguish between infinity and does not exist. In my case, since you in physics, especially high school physics, you never run into a vertical tangent, I honestly don't care whether you call it does not exist or infinity. Okay, so that's it for me talking, at least for a little while. We're going to queue up 2 more Khan Academy videos, and then I think that's going to be there's just going to be a little bit of wrap up and some homework, a video to help you out on the homework. All right, so see you in a few videos.